1.
Welcome, everyone. Welcome to our 4th Aviation Reimagined webinar series, coordinated and hosted here by Griffith University. We've had over 400 people register from all over the world, representing industry, airlines, airports, government, universities, consultancies, and interested individuals. Griffith University acknowledges the traditional custodians of the land on which we live and are meeting today, and pays respects to elders past and present, and extends that respect to all Aboriginal and Torres Strait Islander people. So this is our 4th and final of the 4-part series, which is run every Thursday, 3 p.m. Brisbane time in October. We'll put a link in the chat functions for anyone who'd like to see the content from the first 3 webinars this month. So this webinar series responds to the urgent need to reduce emissions in tourism and transport and to inspire collaborative action in Australia. We're looking to share and investigate emerging policy, practice, research and developments, and to facilitate discussion and dialogue. So I'm Tim Riley, Professor of Aviation at Griffith University, and I'm facilitating today's session with Suzanne Becken, Professor of Sustainable Tourism at Griffith University.
Good afternoon, everyone, from me as well. Today, the session is about technology, innovation and advancement, obviously absolutely critical to advance the decarbonisation of the aviation sector and also to increase resilience. Today, we will hear about new aircraft design, engine and powertrain design, renewable energy and fuels, air traffic management, rethinking airport infrastructure, ground support efficiencies, and of course, the emerging role of artificial intelligence. The session today will explore all options from retrofitting existing infrastructure of aircraft right through to clean sheet designs, all with an eye onto the target of 2050 net zero emissions for the aviation industry. Now, just like with all the other sessions, we have 3 presentations to start with. And at the end of the session, we have time for Q&A. So if you have any questions popping up while you listen, please put them in the Q&A box. If they are for a particular speaker, you can direct them, and then we will have plenty of time to discuss them. Just a reminder to everyone that we do record the session, and you can access the link afterwards on our webpage and also share with anyone else who you think might be interested. And now I'm really pleased to introduce our first speaker, Professor Simon Weeks. Simon is joining us from the UK, so he had to get up really early, and so we're very much appreciative of this. Professor Simon Weeks has just started his own consultancy business. Before that, he was the Chief Technology Officer for the Aerospace Technology Institute, responsible for the UK's aerospace technology strategy and a rather large program worth over £5 billion. And before that, Simon had held senior engineering and technology roles with Rolls-Royce, including the global head of aerospace research and technology, director of engineering operations for aero engine controls, technical director for Eurojet, leading development of the EJ200 engine for Eurofighter Typhoon. Simon is a visiting professor in engineering science at Oxford University. He's a chartered engineer and a fellow of the Royal Aeronautical Society and the Cambridge Institute for Sustainability Leadership. Simon will present on some of the technological advances behind alternative fuels and wider issues that might affect the speed of implementation. So we're very excited to hear about this, Simon. Without further ado, I pass the floor to you.
Thanks, Suzanne. Just checking you can hear me okay. And well,
Perfect.
Good morning. Yeah, good morning as it is from me from the UK. Very early, I had to get up very early, as my colleague said in the morning, to join you. Okay, so really great to be joining you this afternoon, your time. And I'm going to tell you just a bit about, few of my experience and knowledge on aviation technology for zero climate impact. So next slide. So we'll start actually with the sustainability impact of aviation. And as I'm sure most of you know, two main impacts of aviation on the environment today, on the climate, which is the, if you like, the global atmosphere around us, and then local to airports. And I think you know, the main topic, obviously, of today is climate. Aviation is somewhere between about 3.5% and 5%, depending how you look at it, on impact on climate change. About a third of that, only about a third, is CO2. And now it's thought that the major impact, or the biggest impact, is actually from contrails, probably about you know, certainly about half. And then you've got NOx emitted in the upper atmosphere, which is also a climate change agent. And I believe in one of the other webinar sessions, there was actually quite a lot of detail, or there will be quite a lot of detail on the science around contrails and climate. So, okay, but I think what we'll see is that this focus of this presentation is largely around CO2, because there's not actually, and you know, the science is relatively poorly understood, I would say, on contrails. It has developed a fair amount recently, but still some way to go. Okay, next slide. So I think one of the overall straplines is really there's no silver bullet to address the climate change impact, the sustainability impact of aviation. To address that, you need to look at all aspects of the air transport system. And I know some of my colleagues who will be following will talk about some of those broader aspects of the system. So I won't dwell too much on those. My main focus is on addressing air vehicles and also the power sources that we're going to use to power them in the future. But really important is the way that we also fly our aircraft, and you can adopt much more energy efficient pathways through the sky, if you like, as part of flight operations, and deal with the emissions on the ground of aircraft and so on and so forth. But you've also got the emissions from manufacturing, ground, other sorts of ground operations, airports and so on, and from through life support. So next slide, please. So key things really to address climate change. So at the top of that, really my first priority is to increase the energy and resource efficiencies. It always makes sense to do that. People get all excited about all sorts of sustainable fuels and so on, and they are coming through for sure. But it always makes sense to increase energy resource efficiency, because the more efficient my aircraft can be, the less sustainable fuel I need, which tends to be more expensive. So always makes sense to do that. And then next, to develop sustainable alternative fuels. Those are becoming available now, although not in large quantities. And then move to non-carbon energy sources. So here I'm thinking about batteries and hydrogen, and lots of excitement about hydrogen in the world at the moment. Next slide, please. So on aircraft energy efficiency, so 4 key things really to focus on there. Aerodynamics of the aircraft and engines to make them more efficient. The thermodynamics of engines, so running engines to much higher pressures and temperatures improves the thermodynamic efficiency. The aircraft systems, electrical power efficiency, and then obviously weight of the aircraft and its systems and engines. Next slide, please. So what can we use to power future aircraft? So when I was in the ATR, we did quite an extensive exercise looking at options for powering aircraft in the future. And as you can see along the top, some of the alternatives there, right from batteries, fuel cells, powered by liquid hydrogen combustion, using gaseous hydrogen, ammonia, and then finally sustainable aviation fuel. And what you can see is there's no perfect solution to anything. There's a red on every column, and some of those reds are redder than the others. So we'll take a little bit more look in detail at the differences between batteries and hydrogen. But one we eliminated pretty early on was ammonia, and largely because its fuel and propulsion system mass is not that favorable. Also NOx emissions, and also handling it in large quantities on the ground and in the air. The view was there that it was really not a suitable fuel for aviation. So we eliminated that one fairly early, which takes us forward with batteries, fuel cells, batteries, hydrogen, both in a fuel cell and combustion, of course, and sustainable aviation fuel. So if we go on to the next slide. So how would we make those sorts of choices? Well, it depends on really what sort of aircraft you want, how much payload you want from that aircraft, and how far you want to fly it. And the key aspects of energy sources and the way that you convert those energy sources into propulsive power is around the propulsion and energy system power density. The most power dense, the most energy dense systems are modern ultra-high bypass ratio gas turbine systems. You can see a little picture of one there. That's Rolls-Royce's latest offering in the pipeline in development at the moment. It has been running on the test bed. And you can power those very large gas turbine systems with both sustainable fuels, and you could fuel them in the future on hydrogen. And as we'll see a little bit later, hydrogen, you're going to have to use liquid hydrogen to get you any appreciable distances in an aircraft to get the density there of your fuel storage. In the middle there sits hydrogen fuel cell systems. They're not as energy dense or power dense as gas turbine systems, but they do potentially offer some advantages for smaller aircraft. So from fuel cells, you won't, for example, see any NOx from high temperature combustion because you're not burning the fuel, you're converting the chemical energy in an electrochemical system in a fuel cell. But obviously you've got the weight of all the components of that propulsion system to worry about: the fuel cell system itself, electric motors, power converters, and electric cables, which can be very heavy. And then lastly, battery systems down on the bottom left. They are the least power dense of all the propulsion options, but have the lowest potential environmental impact of all. And actually, in terms of efficiency, they're the highest efficiency way in terms of conversion efficiency to store electrical or to store power on an aircraft. So those are the options, and as I said, it depends on how much weight you want to carry on your aircraft, how much payload, how many passengers, and how far you want to fly. Okay, next slide. So let's have a little focus on SAF at the moment, because with SAF, sustainable aviation fuel, that could be used in any gas turbine aircraft flying around today. Effectively, it's allowable up to 50% on any aircraft. If you want to go above 50% blend on SAF, you need to make some modifications to the fuel system to do that, but it's perfectly possible. And aircraft in the future will all be SAF compatible. And if you think about it, this is the most straightforward thing to do in terms of the aircraft itself. It's almost a drop-in, and you don't really need many physical changes to the aircraft. In fact, at a 50% blend, you can use it without change. and it is reasonably readily manageable in today's fuel logistics and storage systems and so on. Where does it come from? Well, from sustainable biomass sources, so growing crops that are can be converted chemically into molecules that look like the molecules from fossil fuel, and also from waste biomass sources. So people are looking at recycling waste products also into bio-derived SAF. And this picture just shows you the elements of the, if you like, the life cycle. And you do need to think that you are emitting CO2 all the way through that life cycle, in transporting elements of that, sorting, processing, converting, and refining your bio feedstocks, transporting it, and so on. All consumes some energy, and all of that will give you some residual CO2, as well as the bulk of the CO2 that you generate when you fly. So you do need to take that whole life cycle into account when you're totting up the net zero or the net carbon dioxide impact of that whole life cycle. But the other thing I'd point out is that aviation is in competition for the feedstocks for biofuel, so competing against road transport. So at the moment, in most countries in the world, there's legislation that mandates a certain minimum amount of sustainable content in road fuel. Aviation doesn't have that at the moment, so that'd be a great starting point for aviation to have that. So next slide, please. So the other route for sustainable fuel is actually to synthesize it. So here you're making fuel directly from carbon dioxide, which you can capture from the air. That takes quite a lot of energy. Or you can extract carbon dioxide from the exhaust streams of things like steel making, and concrete making, and so on, very high CO2 emitters. And you combine that with hydrogen, and the hydrogen you get from green sources, largely in the future solar power or wind power, or nuclear power even, and converting that to hydrogen by electrolysis, and then going through chemical processing to synthesize a kerosene effectively. And then you can put it into the conventional logistics network. Again, it could be blended up to about 50% with fossil fuel for aircraft that aren't adapted. But in the future, newer aircraft will be fully SAF, 100% SAF capable in the future. So that's PTL, power to liquid, SAF. Okay, next slide, please. On to hydrogen. So huge amounts of interest at the hydrogen. Why not use hydrogen to power an aircraft directly, rather than going through all sorts of chemical processes that consume energy? Over on the left-hand side, today, pretty much all of the world's hydrogen is either what's called grey or black. These are the colours of hydrogen, the types of hydrogen. And grey hydrogen is steam reforming. This is where you use natural gas in a chemical process. The chemical process strips the hydrogen away from the natural gas to use the fuel. But obviously, you release the carbon as carbon dioxide. And a similar kind of idea from coal, gasification process. Both those are carbon emitters. They have the same, about similar climate change impact globally as all of the carbon emissions from aviation. So that's also a problem at the moment. But there are more environmentally friendly ways potentially to make hydrogen. I think probably the best of these is green hydrogen. Obviously, this is producing hydrogen by electrolysis, and your source of power, electrical power to do that, are from renewables. Equally, you could use nuclear energy. Then there are also a lot of people talking about so-called blue hydrogen. So this is the equivalent of grey, but you're capturing the carbon, sequestering it underground. Also, you can make hydrogen through high temperature pyrolysis, which just rejects the carbon as a solid, or so-called yellow hydrogen, which is producing hydrogen from solar energy. So that's the colors of hydrogen. Next slide, please. This chart just shows a more detailed view of that. So it just really points out that you do obviously have a chain to go through for hydrogen, just like other liquid fuels. Obviously, for aircraft, we're talking about to go longer ranges, not just using hydrogen gas, but converting that to a low temperature cryogenic liquid. And there at the bottom is the blue hydrogen life cycle. So if we move on to the next slide. Hydrogen is not the easiest thing to store and transport. So over on the left-hand side, obviously hydrogen occurs naturally as a gas. This technology is well known in terms of storing hydrogen. You can store it in high pressure cylinders. For aircraft, you could use composite cylinders. But to get appreciable amounts of hydrogen onto an aircraft, you need to liquefy it. And this is quite a considerable technical challenge. Here you need to store it cryogenically, and it's at over minus 250 degrees centigrade. It will liquefy, in fact, solidify air at that temperature. So you do need to take steps to isolate liquid hydrogen from the environment around it through a sort of double-walled systems to prevent heat leakage and so on, and prevent condensation of air and formation of ice around these systems. Next slide. But actually, people have made some cryogenic aircraft, surprisingly. In fact, Boeing, and this was actually many years ago, they flew quite a large aircraft. It was a drone, and it was powered by a couple of automotive engines, actually specially adapted, but carried a big tank of liquid hydrogen in that rather bulbous fuselage. That was called the Phantom Eye, if you want to look it up. But this year actually had, I think it was the first passenger carrying, there's only 1 or 2 passengers in it, that rather strange aircraft over on the right called H2 Fly, and that's been flying around in Europe, which was a hydrogen fuel cell powered aircraft, but it stored its hydrogen cryogenically. And when I was at the ATI, we had a major study where we looked at design options for powering aircraft in the future of liquid hydrogen. There's a couple of examples. Over on the left, a smaller regional aircraft powered by fuel cells, and over on the right, a large long-range aircraft. But see, the key thing I expect you'll notice is that you've got to carry the hydrogen in the fuselage, and that's because hydrogen tanks, liquid hydrogen tanks, need to be as near spherical as possible to prevent or minimize heat ingress into them. So fuel tanks and wings, which is the case for all larger aircraft flying around today, just won't work. So aircraft do need to be significantly different to accommodate hydrogen. Next slide. Refueling will be a bit of a challenge. So we did some work with our National Safety Agency in the UK, Health and Safety Agency, and they have got a lot of expertise in the handling of hydrogen in industrial settings. And with the work that we did, it looked like you could, it would be a challenge to refuel liquid hydrogen powered aircraft. And those pink zones show, if you like, the exclusion zones for people when you're refueling with hydrogen, which are much larger than kerosene. So today you can quite happily fuel aircraft with passengers on them. You couldn't do that, have you, at the moment, if you were refueling with hydrogen. and it will potentially take quite a bit longer to refuel an aircraft on hydrogen than with kerosene. So that's just an aspect of the handling of liquid hydrogen. Okay, next slide, please. Lastly, batteries. And the problem with batteries is that battery systems are much larger and heavier for the same duty that you might get from hydrogen or from kerosene or SAF. And some comparison figures there. There's the sort of rather funny cartoon that's been going around for quite a long time that is saying it, and this is even at if batteries got to 1,000 watts a kilogram, which is the long-term aim. There's still some way away from that. An all-electric Airbus A320 would require 170 tons of batteries, and in comparison today, there's a picture of a 320 there on the right-hand side. The aircraft weight's only 44 tons, and that carries 19 tons of aviation fuel. So there's a world of difference there, almost an order of magnitude difference in terms of the if you like, the mass of the energy storage to go appreciable distances. And so that's why batteries tend to be restricted to shorter range flights. Okay, next slide, please.
You've got a couple more minutes, Simon.
A couple more minutes, yeah.
If that's all right.
So just some pictures here, and people have no doubt seen pictures now of early demonstrators from across the world. These were some of the UK battery and hydrogen-powered demonstrator aircraft that the ATI funded. So on the top left there, you can see Vertical Aerospace. They've been, we're actually flying their prototype around. Unfortunately, they had a little bit of a mishap with their prototype, first prototype, but the second prototype now is well in hand and will be is much improved, and we will be flying around soon. And bottom left is the Rolls-Royce electrically powered aircraft. They got the world speed record for a battery-powered aircraft a little while ago. And over on the right-hand side, there's a company in the UK called Zero Avia, and they've been working on developing fuel cell-powered aircraft, hydrogen fuel cell. So both of those aircraft have flown, and the one at the bottom has been flying around quite regularly in the Cotswolds area of the UK. Next slide. Really, as we said, it's not an easy route to take carbon out of aviation. And the simple part of this chart is that at the top, if you like, the top part of that line shows if you did nothing, that's what would happen to carbon, assuming now the industry is recovering, which it is, and starting to grow at the rate it was pre-COVID, about 4.5% a year. The small two wedges at the top, in fact, show the impact potentially of making aircraft more efficient, and then hydrogen only really coming in towards the 2050s. The purple, large purple sort of area in the middle is biosaf, and the view is probably biosaf can provide half the need of decarbonisation in the future at best. So that means you would need to bring through PTL, which is the light blue area at the bottom, if you fully wanted to mitigate the effects of carbon by 2050. And hydrogen really only starting to make a showing by towards 2050 and beyond. So the next slide, please. I think we'll go on to the final slide. And again. No, next slide. Thank you. So let's just summarize. Again, no silver bullet. All aspects of the aviation system need to be addressed to address the climate. Always makes sense to make systems more energy and resource efficient. SAF needs to be accelerated. It will benefit any gas turbine aircraft flying around today. and gas turbine aircraft in the future. Power to liquid, SAF will be required to fully address decarbonisation by 2050. Green hydrogen powered aircraft could eliminate carbon dioxide, but formidable technology and economic obstacles need to be overcome, both to power aircraft with liquid hydrogen and to put the logistics and handling system in place to transport it around to airports and store it at airports and deploy it. Larger hydrogen-powered aircraft won't be available in sufficient numbers to significantly impact CO2 by 2050. Battery power is only suited to small, short-range aircraft. But just to point out, aviation will be competing against other sectors for SAF feedstocks and green hydrogen. Aviation doesn't have a right to these things. It's going to have to compete for it. And finally, the climate change of impact of contrails is still poorly understood, and more work is required to develop robust solutions in the future. Thanks very much.
Fantastic. Thank you very much, Simon. That was a really interesting presentation and a great start to today's session on the different kind of fuels and the technology behind them. There are quite a few questions already in the chat. If you are able to respond by typing in. Yeah, feel free to start typing in during the rest of the presentations, and then we'll bring you back with the other two at the very end for a verbal Q&A. So thanks very much for that, and feel free, those attending, to type in questions for the next speaker as we go through as well. There's some really good questions there already. So I'll just introduce our second speaker. He's joining us from Sydney, from Airbus. So Stephen Forshaw will talk about different initiatives in terms of technology pathways being developed, ecosystems approach being implemented, and partnerships being progressed as Airbus works towards its net zero carbon emissions objective by 2050. So quick biography. Stephen joined Airbus in 2022 as Chief Representative and Head of Country Australia, New Zealand and the Pacific. He's a member of the Airbus Asia Pacific leadership team and responsible for representing Airbus at a corporate level, covering all the business divisions. Prior to Airbus, Stephen held senior roles with Temasek, Microsoft, Singapore Airlines, and was Chief of Staff to Deputy Chief Minister of the Australian Capital Territory. Stephen has been appointed by the New Zealand government as well to the Sustainable Aviation Aotearoa SAA leadership group and represents Airbus on the Australian government's Jet Zero Council. So the floor is yours, Stephen. Look forward to your presentation. Thank you very much.
Thank you, Tim. Good afternoon, everyone. Thanks very much for joining for this discussion this afternoon. You see here, I took the opportunity to put a picture of Brisbane on the front, probably a picture of Brisbane that many of you will not have seen in this shape before, but just a way to introduce myself to you, which Tim has kindly already done. So we might move forward. A lot of the conversation I'm going to be having with you this afternoon is going to be somewhat similar to what you've already heard. So I'm going to try and skip over some of the areas that have been covered by our previous speaker, other than to say that almost everything he's presented accords exactly with Airbus's view as well. And this is, I guess, an indication of some of the complexity that we're going to be dealing with as we embark on pathways to a more sustainable aviation industry in the future. And I'll come back on that. First, just a little bit about Airbus. We are probably best known for the manufacturing of commercial aircraft. That's probably what most people see, but we also have a very large defence and space business. The space business was actually the pathway through which I got the picture of Brisbane on the front of this presentation. And we're also a very large manufacturer of helicopters. So we have a number of touch points right across the entire aerospace sector. And you see here, in the last few years, we've been spending some time redefining our purpose as an organization. You see here that we have landed on the view that we pioneer sustainable aerospace for a safe and united world. That what that's actually saying is that at the core of everything we do now, embarking on a more sustainable aviation sector is key to everything. So we're spending a lot of time on this. We have a huge amount of resource going into exactly the issues that you just heard from your first speaker this afternoon, including hydrogen-powered aircraft, including sustainable aviation fuel, and importantly and immediately, the next generation of aircraft products that are more efficient and more emission friendly than past generations. If I can move forward to give you an indication of what they look like. So you see here a couple of the wide body aircraft that we're probably best known for. These are next generation aircraft. So when you hear me talk this afternoon about next generation aircraft, these are essentially the most modern passenger aircraft, the ones that we're building now, and are gradually starting to replace some of the aging aircraft that you see in fleets operated by airlines all around the world. This is an important point because it takes a long time for an airline to change its fleet. It's very expensive to buy new aircraft, and we can only build them so fast. So on average, you tend to find that airlines buy new aircraft maybe every 10, 15 years, sometimes every 20 years or even longer. That's because the capex they're required to commit to new aircraft is incredibly high, and they have to balance their operating budgets. But the second thing is that the manufacturing process for new aircraft is a very long one. And if you came to us today and said, I want to talk to you about buying a new A320, a single aisle, 150, 180 seat aircraft, the most common aircraft we manufacture, we're probably going to be talking to you about delivery slots in 2029 or even later. That's how far in advance the bookings are actually taken and made for the acquisition of new aircraft. If I can just move forward to the next slide. You see here the current generation of aircraft that Airbus is manufacturing. Now, all of the aircraft on this slide and the comparable aircraft from our competitor Boeing, like the 737 MAX, the 787, these are next generation aircraft. The distinguishing factor around these aircraft is that they're generally operating very new engine technology. So the technology in the engines is much more fuel efficient than past generations. The aerodynamics of the aircraft have been improved with design, and especially the weight of the aircraft is being reduced by the use of composites and carbon fiber material. And as you would have gathered, one of the key determinants of fuel burn and fuel consumption is the weight of the aircraft. So if you can take weight off the aircraft, then you're able to get fuel consumption and fuel burn down. So that's something that a lot of effort goes into between ourselves as aircraft manufacturers, and I include my friends at Boeing and Embraer and some of the other manufacturers there, but also the engine makers such as Rolls-Royce, Pratt and Whitney, GE, and Safran, and a number of the companies that make aircraft engines for both commercial, military, and helicopter aircraft. This generation of aircraft that you're seeing on this slide are, as I say, the new ones. And there is generally about a 25% improvement in emissions, in a reduction in fuel burn on a seat kilometre basis between a new generation of aircraft and its previous generation. And that tends to have been happening fairly constantly for a number of years. You know, the industry does get better at design, at improvements in efficiency and so on. Yet today, only about a quarter of the aircraft in service are these next generation of aircraft. So, you know, it takes, as I said earlier, a long time to replace fleets. And this process is really important as we start seeing that older aircraft are retired. Then growth in the airline industry can actually be offset by the introduction of new, cleaner technology aircraft that mean that the emissions can actually start coming down. So airlines like Qantas in Australia that announced a major order of our aircraft quite recently. If we move forward to one of the next slides here, you'll see here what the new Qantas aircraft look like. The A220, a smaller aircraft, the A321. These two aircraft will replace eventually the existing 717 and 737 fleet. And then the larger A350 that they'll use for long range, international and ultra long haul, including for the first time the flights between the east coast of Australia and London and New York non-stop. Now these aircraft are, as I say, next generation aircraft. As airlines like Qantas embark on fleet replacement, they retire older aircraft, they take them out of the system, and that's a good thing. One of the things we have seen since COVID is that COVID actually was an opportunity when airlines were grounding their fleets for a number of the airlines to begin and accelerate retirement processes of older aircraft and introduce newer aircraft. So even during COVID, some airlines still continue to receive new aircraft. They weren't flying them, but they took the delivery of the new ones so that when they recovered and started operations again, they were able to retire their older aircraft. So this fleet replacement is really an important composition, an important part of the decarbonisation journey, and is happening today. So, it does go to show that those airlines that are investing in fleet replacement now are actually taking very seriously the issues of decarbonisation. If we can move forward. So I'm going to spend a little bit more time now on the sustainability roadmap. Move forward. You'll see here a slide that I think touches on some of the things that Simon just talked about. We are actively working on what we call our Zero E program, which is essentially hydrogen-powered aircraft. And you see here a number of concepts of what those aircraft look like. And they're actually very similar to what Simon just showed you in his presentation. You'll see the windows at the front, but then a pretty significant part of the fuselage at the back where there's no windows, and that's actually where the fuel tanks will sit, just as Simon explained. Then at the front, you see the concept aircraft that looks more like something out of the Jetsons. And this goes to the point that Simon was making about how you can't use the wings for fuel storage. So actually, what might a new generation hydrogen-powered aircraft look like? It may actually mean a completely different aerodynamic design where the fuselage is much bigger and the wing space blends much more into the fuselage than it does on existing aircraft. Now, to be very clear, hydrogen is still a very long way off. I agree with Simon on this. It's going to be a long-term possible solution, but it's going to be step by step, increment by increment. We're expecting to offer a zero-emission commercial aircraft, as you see here, by 2035. But to manage expectations on that aircraft will probably be a very small one. It will fly short distances and carry few passengers. It is why we're looking at markets like New Zealand as ideal for the operation of those aircraft, because they tend to have in New Zealand those shorter routes, less dense routes than we do here in Australia. If I can move forward. And this slide, I think, covers exactly what Simon just spent time on. The battery and electric model is probably going to be for small aircraft. I would suggest helicopters and commuter aircraft, very short distances. Drones will be, especially as we're already seeing, drones will be very much powered by battery electric. And then the two forms of hydrogen that Simon talked about, gaseous hydrogen and liquid hydrogen, will play a role for perhaps short to medium haul, slightly more passengers, but still not the density that we're used to seeing in the commercial aircraft space in large aviation markets like Australia. That's where SAF comes in. And we take the view that SAF is the immediate solution, but we are nowhere near the levels of maturity in production of SAF that we need to be to help bring carbon emissions down. If I can move forward. So CO2 reduction, essentially, this is a simplification of an overall strategy around greenhouse gas reduction. First, at the top, you'll see the technology and design issues. That's what I've just been speaking about, the design of new aircraft, new engine technology, next generation technology. Then, hydrogen on the left, I've just talked about. SAF is going to be the essential move from short to long term in terms of decarbonisation. I'm going to touch a little bit more in a bit more depth on SAF in a moment. Airport infrastructures and operations and air traffic management, I think we touched on these in Tim's opening at the beginning, but things like how we operate aircraft, how we fly between cities, how we operate aircraft on the ground at airports, how air traffic management sequence aircraft in airspace, departures, approaches, and these type of things. All of these can still generate more efficiencies. Globally, we estimate that that could be as high as 8 to 10% of emissions could be tackled by making operations more efficient. Um, that probably has differences in different parts of the world. So I would argue in Australia and New Zealand, where we're actually pretty efficient at managing our airspace, the reduction opportunities here may be less because we're already doing a lot. But in other parts of the world, there's still a long way to go in terms of making our operations more efficient. I've often said that if I, flying into London, wanted to see Windsor Castle 3 times, I'd actually go and visit it. I don't need to fly over it 3 times as we circle around and around waiting for an approach path. And this opens a whole question of how we measure airline performance. Today, we measure airline performance judged on on-time departures. But actually, there may be good reason why holding an aircraft back from a departure schedule could actually lead to fewer emissions and a more efficient flight path, and sometimes even can still meet the same arrival time by leaving later. So, we do have to have a conversation around what are the right performance measures if we really want to tackle emissions and recognize that sometimes a more agile and efficient way of managing airspace operations could lead to changes in schedule. As inconvenient as that may be sometimes for customers, it's actually going to have a net benefit for the environment. And that's something that we ought to at least have a conversation around and consider pretty carefully as part of the mix. And then economic measures that I show there at the very end of all of this, we have to assume that we're going to make an inroad on emissions that's going to be pretty good if we can do all of this together, but we'll never get to zero. So at the end of the day, some economic measures such as offsetting may be still required to ensure that the industry can really truly get to a net zero position. Our view at Airbus is that that's the last mile, not the first mile. So offsetting is not the answer to making the industry more sustainable until and unless we've done all of the things that I've just been talking about first, and then offsets play a role at the end to cover the last mile of very hard to abate emissions or areas where we just don't yet have the technology or the science to be able to achieve. I think Simon touched on this when he talked about what's going to be required to move aircraft to 100% SAF operations. There's also, on top of the technical issues that Simon addressed, issues of certification. We've, I think, globally achieved a very good standard of safety across aircraft operations by ensuring a commonality of standards in the certification of aircraft engines and components. And so whenever changes are made to aircraft technology, including airspace design and aircraft design, an exhaustive process is used to certify those changes as safe. And that's a good thing. It's expensive, but it's a good thing for us as customers. The same thing will have to happen with SAF, and the same thing will have to happen with hydrogen. So my point here is that we all have high expectations of moving at great speed, but sometimes we have to temper our speed expectations because of the need to properly certify and study the impact of what we're doing. At the end of the day, science and research is going to deliver us the answers to this challenge, but science can't always be rushed. Let's move forward. So you saw a chart very similar to this that Simon just showed. I call this the lasagna chart, but this one I orient slightly differently because I'm looking here at the pathways to get us to zero, including all of the other things in there like air traffic management and then finally offsets. But you'll actually see that the numbers may differ, and I think we'll all have slightly different views about what the ultimate composition is going to be to get to zero. But the important point here is that we're agreed on what the inputs are that are going to get us to net zero. In my chart here, I do actually still include a pathway for offsets. But at the top, the light blue segment, that's that new aircraft technology that I talked about. And then the dark blue is disruptive technology. You'll see that that doesn't kick in for quite some time yet. When it does, it will eventually grow to be a much larger slice of the pie. And that basically is hydrogen, but hydrogen is still a long way off. The airspace and air traffic management we show here as 7%. As I said earlier, it will vary region to region. SAF is the big one, 53%. SAF is still, we are producing 0.01% of global aviation fuel demand today as sustainable aviation fuels. Simon accurately highlighted that there will not be enough biomass to be able to produce the aviation fuel we require on top of all of the other fuels that are going to be competing for that same biomass for conversion to renewable fuels or sustainable fuels. But in order to do SAF, in Australia, for example, we're producing none. So we consume somewhere between 9 and 10 billion litres of aviation fuel a year. At the moment, it's at the lower end. By 2030, it'll be at the upper end of that. So even just to get to a target that the industry is talking about of 10% use of SAF by 2030, we need to be producing 1 billion litres of SAF in Australia every year, and today we're producing none. So that's why ourselves and Qantas have each embarked on a program where we're jointly investing $200 million into businesses in Australia that are seeking to create a SAF production ecosystem in the country. Producing SAF here in Australia, using the biomass, generating the hydrogen to produce eSAF, the types of things that currently we're not doing, that currently there's not enough government support to be able to do. Look, even as we commit these funds, we're struggling to find the opportunities that can deliver SAF very quickly. So a message that I repeat to stakeholders, to governments in the region, is the urgency of getting a SAF industry up and going in Australia is critical. We have biomass here, but if we don't have production, what's going to happen to that biomass? It'll, of course, be hoovered up and exported overseas. And by the time we get to a point where we're actually starting to produce SAF, we may find the biomass that we did have is no longer available to us. Now, we do have a rich opportunity with green hydrogen because Australia has access to vast amounts of solar energy, and solar energy will be a great catalyst for the production of hydrogen. And in turn, I would submit that the priority of the production of e-fuels needs to go into aviation because unlike other sectors of the economy, unlike other forms of transport, aviation will find it very, very difficult to mitigate or abate our emissions in any other way in the short to medium term other than using SAF. With motor transport, land transport, batteries are a very good option, are currently available, and as battery technology gets better, then range will go further and so on. But that opportunity for aviation is very limited. So we really do need this multifaceted approach to bring it all together to create and catalyze a SAF industry here in Australia so that we don't get left behind in the global rush to produce sustainable aviation fuels. We're the 9th largest market for the uplift of aviation fuel in the world right now. And why is that? Of course, nearly every flight here is a long-haul flight, so everyone needs a lot of aviation fuel. We're producing next to none of it in the country. We're actually producing very little by way of fuels and refining of fuels here in Australia today. We have an opportunity with the availability of biomass feedstock and with the opportunity to use green hydrogen to produce SAF to actually turn this into a domestic fuel industry and create very, very strong energy security for Australia going forward. But we really have to start making those investments, start catalysing those opportunities to develop production here in Australia now, not in the years to come. You start building a refinery tomorrow, it's going to take at least 3 years for that refinery to be operating. And so, we're already being left behind. We can't afford to be left behind any longer. If we can move forward. So I touched on, and I just want to come back to the slide that I showed earlier on how we're seeing the potential new generation, just to close out this presentation this afternoon, and share with you what the future could look like. Hydrogen is going to be a fascinating potential fuel for aviation, but I think much like Simon has said, this is still a long way off, and it doesn't provide the immediate answers to how we can decarbonize our industry quickly. But what it does do And what it will open up is the opportunity for more research and development to be able to move to a true zero emission flight path for aviation going forward. Thanks so much for having me this afternoon.
Thank you, Stephen, for this, simultaneously inspiring presentation, but also some reality check in terms of timelines. It was really, really great to hear about that. Our final speaker is joining us actually from Japan today. Let me introduce to you Alexander Ferret, who's the CEO and founder of Open Airlines. Open Airlines is a French software company that developed Skybrief, the leading eco-flying solution based on big data and AI. Skybrief is used by 58 airlines now worldwide, and it helped to save 1 million tons of carbon dioxide already just in 2022. Alexandre has a master's in computer science from the École Centrale Paris. He started his career at IBM. Research in New York in the US, and before opening this new company, Open Airlines, he worked at Air France as the lead architect of the operations control center and the crew management IT department of the company. So quite a new topic here for our webinar series. Alexander, we are very excited to hear from you. Over to you.
Thank you very much. So thank you. So I'm going to complement to Simon's and Stephen's presentation with a focus on operations that they quoted. And our mission at Open Airlines is to accelerate aviation's transition to sustainable development through digital technology. And today I will explain how AI and big data can help achieve that. First, if we take the airline's point of view, today's situation is very challenging. The airlines are under a lot of social pressure. Here in Europe, there is an anti-aircraft movement that has its own name, Flixskam in Swedish, because of Greta Thunberg. And airlines in Europe have seen changes in the way people use air travel. The young people are traveling less because of flight shame. But even more rapidly, the corporate world has changed habits. A lot of corporations in Europe have put in place ESG policies where they encourage people to do more video conference or to take the train. So that's the first pressure. The second one, obviously, is the environmental pressure. We talked about it. If we do nothing, CO2 emissions are going to increase by 45%, and they are already about 3% of the total CO2 emissions. And finally, as you all know, the aviation industry just got out from its worst crisis. And it's basically cashless and full of debt. It's doing fine today because traffic is picking up and they have good revenue. But there's a lot of economical uncertainty, and the price of energy in particular is putting a burden on them. But the worst is to come, I would say, with this challenge to be net zero by 2050. We saw how it's going to be challenging in terms of technology. We have hopes. We have these people from Airbus that are developing new aircraft, but it's going to be very challenging and very costly. Also, from an environmental point of view, we saw that the disruptive technology will not kick in before 2030 and 2035. The hydrogen aircraft or the electrical aircraft for small places. So by then, what we can do is SAF, of course, but they are not today, they are tomorrow. On operational efficiency, in the end, we saw that it could be 9%, but by 2030, it's probably one of the largest part or easier to get part at least. So that's where we are focusing on, these 9%. What's important is what we can get them today. And it's important because a kilogram or a ton of CO2 that we release today is going to warm up the atmosphere for 100 years. So what you can save today is probably more important than what you can save in 2030 or 2050 to reduce the climate change and the heating of the Earth. The good thing also about operation is that it's probably the less costly for airlines, at least. SAF are 3 to 5 times more expensive than kerosene. And if you save 9% of fuel because you are improving your operations, basically you reduce your cost by 9% almost. So it's very interesting for airlines. So what are these operational improvements? To make them easy to understand, I've given some examples. It's nothing new. It's things that airlines can do, ATC can do, just to operate the flight in the same manner but in a more efficient way. These are well known, but are not always done. For example, when an aircraft has landed after the engine has cooled down under certain conditions, you can shut down one engine and taxi with just one engine. You're going to save fuel. When you land, you can use reduced flaps. And in this case, you still have a required lift to land safely, but you reduce drag and you save fuel. Traditional approaches are what we call step descents, where you are going to burn more fuel and make more noise. If we can, with ATC, do more continuous descent approaches, we save fuel and make less noise. So there are many other examples like that. So I'm sharing a list here of industry best practices. There are many. They can concern flight ops, the way you fly the aircraft, dispatch, the way you prepare your flight plan, or engineering and maintenance, which is the way you prepare your aircraft. Things like engine washes, for example, will improve the performance of the aircraft and reduce its fuel consumption. For flight planning, better route planning based on weather and traffic conditions can be more efficient, save fuel, and save time. And even on the ground, you can save fuel. For example, if you plug your aircraft to the electrical network, then you can provide electricity to the aircraft or air conditioning to the aircraft without using the engines, and thus reducing the fuel consumption and CO2 emissions. So these best practices are well known, have been described by the industry, by IATA, by Airbus, by Boeing, but airlines are often clueless about which one makes sense for their operation based on their networks, based on the aircraft they are operating, and the environment where they are operating. As Steven says, operational efficiency can be dependent on the geography where you are operating. If you want to know more about these best practices, we've written, I've co-authored a small book called the Green Airline Fuel Book, which gives you a lot of details about these best practices and some information on how to apply them. And you can download it freely on the internet. So I've put the link here. Feel free to download it, read it, share it to other people to educate the whole industry. Now, how do we use technology to facilitate the application of these operational improvements? Well, first you have to realize that CO2 avoidance in an airline and beyond the airline in the aviation ecosystem is a team's game. So you have to embark all the people that can have an impact on the efficiency of your operations. So that's why we have developed a solution called SkyBrief that gives a 360 degrees views on operational efficiency. And we want to engage people such as, flight ops engineers, obviously, pilots in the briefing and debriefing, but also on board, controllers that can have a large impact also on efficiency of your operations, and people in the maintenance shop, when I gave the example of engine wash, for example. And in the end, a key success factor is to engage all the stakeholders around a common CO2 avoidance culture. I like the lasagna chart where we saw that we needed all the pieces of technology. We need also to have all the people who are operating an aircraft or giving the air traffic control services to the aircraft, the airport, to work together. So now a little word about the innovation and where big data and AI takes place and how does it work. Well, the principle first is that we gather a huge quantity of data. Basically, we gather all the data from the flight data records, the black boxes, all flight plans, air traffic constraints information, weather information, and we gather all this data with terabytes of data. We have already analyzed more than 5 million flights in a common database. And then in a European research project called Clean Sky, we've developed algorithms based on performance based on physics, but mostly based on AI, on machine learning, to find out whether an airline could perform best fuel-saving best practices, whether they did it, or where there are opportunities to be grasped. Once these computations are done, airlines and all stakeholders can do a lot of analysis to find out where they should make progress and to monitor their progress. And what's very important also is to empower all the people on the ground, in the cockpit, and we do that with mobile apps, so that they can take the best decision to have the most, eco-conscious flight. So at the end, it's people that make changes, people that make decisions. So you have to bring this AI generating information into their hands in a very convenient way. So basically, what we do is on each flight, we compute the fuel consumption of a flight. We analyze hundreds of parameters per each second of flight. But with machine learning, we simulate also, we compute what they have saved by applying some best practices and what they could have saved by operating a perfect flight, so to say. We use this motto, you cannot improve what you don't measure. So we start by measuring where you stand, what you've saved already, and your remaining potential. And that gives you insight, actionable insight, on where you can make progress and where you can improve. A little focus on the pilot engagement. I said it's a team's game, but obviously the pilots are the ones flying, and they have a lot of impact on the operations, on the efficiency of the flight. And we want to create a real eco-flying culture and eco-flying skills among the pilot community. And we have equipped all our pilots with a mobile app that they usually have on their iPad, but it can be on a phone. It's called My Fuel Coach, because it acts as a pilot instructor that is specialized in fuel efficiency that sits on their side. And basically, before each flight, they have an eco briefing where we tell them, when they prepare their flight on their route, which best practices they can apply, which improvements they can have during this flight. And at the end of the flight, they have an eco debrief where we'll tell them, how much CO2 they've saved, and they can be proud of that. And we are going to tell them also where they could have done better. And you see in the next slides that once they have this tool in their hands, they make a very dramatic progress in their eco-flying skills. We also have a module that is used live in the cockpit, connected to the aircraft. It's a brand new module that will give them advices in real time during cockpit to perform eco-flying techniques. Now, I will go on with some case studies so that you understand, the impact that we can have today. I will start with this case study that we had at the beginning of our research. We talked with the chief pilot of Transavia. We monitored one best practice, which is called idle reverse thrust. Basically, when an aircraft lands, it can slow down with the brakes or with the engine. Traditionally, people have used the idle thrust to slow down the engine. But with modern aircraft, with carbon braked, it's not necessary. It's necessary only if the runway is very short or if the runway is contaminated. But otherwise, the computer of the aircraft will put the right pressure on the brakes so that it slows down at the perfect speed. So you don't need to use the engine. And if you don't use the engine, you're saving CO2. Well, Transavia was well aware of that. That was their standard operating procedure to do idle reverse thrust when possible. But they were very surprised to learn when we looked at their data that only 44% of the flights were actually executing an idle reverse thrust. Most of them were still using, the past procedure, which was full reverse thrust. So they explained to the pilots that they don't need to do that, conditions permitting, that the computer is going to optimize the way brakes are applied to slow down the aircraft. And they started with a campaign, and very quickly, people started changing habits. And after a couple of years now, almost all of the flights are performing idle reverse thrust. So fuel efficiency is it's small numbers multiplied by big numbers. Small savings, couple of kilograms of fuel per each flight multiplied by a large number of flights. And we computed that this single best practice, going from 44% of application rate to 93%, it was saving the airline $15,000 US, So we're speaking of decarbonizing and saving money. And more importantly, they are saving 50 tons of CO2 per aircraft and per year. Another example, I mentioned how you could perform single engine taxi, especially when you taxi in and go back to the gate. So it has to be done under certain conditions. You have to wait until the engine slows down. You shouldn't cross any runway. You shouldn't have any sharp turns. So there's a little bit of skills to be acquired. But it's a common best practice. And when we started working with Aerolíneas Argentinas at Buenos Aires, they were aware of it, but they were doing it only 16% of the time. And we showed them, but based on their conditions, they could do it, much more often. And they started a communication campaign when they started using Skybrave because we computed the benefit. And they reached, 39, 40% application rate, which is quite good. They saved a lot of fuel, a lot of money, and a lot of CO2 doing that. But really, the game-changing point was when we introduced My Fuel Coach, the pilot app that I described earlier. Because as soon as the pilot had this briefing and debriefing flight after flight, they were coached to be more efficient. And very dramatically, in a couple of weeks, in a month, we went from 40% application rate to 71% application rate. So that shows how big data and AI, if it's put into the hands of the right people on the ground or in the cockpit with mobile tools, for example, can have an impact very quickly. Another example this time that doesn't imply pilots, but that looks at maintenance. I explained that with high pressure engine wash, you can improve the performance of an aircraft. And we can measure that also by big data analysis. And this is a chart of the average consumption of each engine of 737 during cruise. So around 1 ton of fuel per engine and per hour of flight. And after the engine flight, this consumption per engine drops by 40 kilograms per hour. So basically they save 80 kilograms per hour or 400 kilograms of CO2 per hour with this high pressure engine. And then as the engine gets dirty, the performance goes down again, and it's time to do another engine wash. So with big data, you can measure that very precisely, and then you can propose what would be the optimal cycle to wash the engines. To finish, I finish with a study that goes beyond the airline in the airspace ecosystem. We looked at approaches at Paris-Orly Airport and the Western approaches in particular. And this diagram shows all these flights that are coming from the West and arriving to Paris-Orly. Each line is a single flight. When it's dark blue, it means the fuel consumption is low. Basically, the aircraft is going down. When it's light blue, the fuel consumption is higher. Basically, the aircraft is flying at step level. And what we can see is that, all these aircraft coming from the left, basically they have two approaches, a southern one and a western one. And ATC gives a lot of directs, which is good, a lot of shortcuts. All the people going on the south way, a lot of them got more direct routes, which save fuel. But what we see with the colors also is that all the aircraft go down very early at flight level 260, and then have large steps before they can continue their descent. And you're probably aware that an aircraft is more efficient when it flies higher, where the air density is lower and drag is lower. So there's a real penalty in having all these aircraft flying down very early during the descent. So we computed, the cost of doing that. Airlines share that with controllers. And now whenever they can, when traffic allows it, they will also allow aircraft to fly higher for a longer time and to begin their descent later. And this is saving a lot of CO2 also. I will finish with one last example, which is also about ATC. That was in Dubai, where basically there's a trombone for aircraft when they are arriving. They follow this curve, to land on the runway. And because traffic was increasing, Dubai Airport decided they would increase this trombone. But at the end, they were giving a lot of short approaches. And Fly Dubai used this data to discuss with ATC and with the airport authority, and they asked them to shorten the trombone again, because actually with the traffic they had, they were mostly giving it. But by shortening the trombone, then it can be official, and you can plan your flight and your fuel and your reserve based on the shorter trombone. And that's also saving thousands of tons of CO2. And that benefits to all the airlines that are now landing in Dubai. To finish, so you said we had 58 airlines. We are growing very fast. So we now have 64 airlines around the world that are using the system, all business models, all types of aircraft. And what we are very proud of is that these airlines last year, they saved 1 million tons of CO2. So for us, it was quite a milestone. And to put that in perspective, the whole SAF industry last year saved 7 times less CO2. So of course, SAF is the future. I know it's going to be huge, but by then, in the present time, operations improvements can be a very efficient solution, and it's also interesting in terms of cost saving for an airline. To finish, I want just to share this QR code. We try to educate the aviation industry and airlines as much as possible on eco-flying techniques. And we have recently designed a small e-learning, which is free for you to take, where you can learn more in-depth, these techniques, these eco-flying techniques. If you are a pilot or just an airline enthusiast, I will encourage you, to go through this course. You get a little certification and spread the word. Thank you very much.
Fantastic. Thanks very much, Alexander. Can I ask all the speakers to join us, please? The Q&A session, we'll have a quick verbal discussion over it. Thanks very much, Alexandra. Yeah, it was great to have big data and AI coming into the session this year. As we kind of look back, this is the final one this year, and actually it was nice to see the people side of it and getting people involved into that with the pilots. I kind of enjoyed that. Also, a big thank you to the first 2 speakers. They've been really busy on the Q&A. I really appreciate their detailed answers. I'm getting smiles and laughs from the first 2. That were really, really good and detailed responses. So I think while Alexander has a quick look, there's a few there for him and for others. I think, and I'll go around in turn from Simon and then Stephen and Alexandra. 2 very quick and straightforward questions. One person actually asked really, really neatly. We've had a lot of the challenges every year. We've run this for 4 years now. The question in the chat was, over the last year, we've had what's been the most interesting thing you've seen? I'll ask a slightly different version. Firstly, what's the one thing looking ahead in technology over the next year that really excites you in this area? And also, secondly, if there's anything from the chat for your detailed responses that you just want to add to your presentation that you may have missed early in the so Simon, can you quickly answer those 2 points? We'll take as long as you want.
Yeah, I mean, the most exciting developments in the near future, I'd say, will be stuff on hydrogen. There are some really, really big hydrogen technology programs in the European scene, both in UK and mainland Europe, in the EU. A lot of money now being spent on hydrogen aviation research, and we'll start to see some really exciting things happening. Lots more aircraft starting to fly around with hydrogen, and even cryogenic hydrogen as well. So I think watch this space on that one. What was the other point?
Yeah, just anything. I know you've been busy frantically in the chat and great answers to it. Anything you want to add from the chat verbally that you just want to chip in that really stands out from the last half hour or so, and what from the other speakers?
Quite a few questions on sort of concerns about if I live by an airport with and they're going to be using hydrogen. There's been 2 or 3 quite detailed reports on the implications of hydrogen at airports, and I direct people. The ATI, on the ATI website, for example, you can access quite a detailed report on the implications of hydrogen on the airport. Hydrogen is more difficult to store in some ways than kerosene. You need a lot more, potentially more area, But one of the advantages is if you get any leaks, it does go straight up because it's less dense than air. So and also there's no smell. So today, if you live by an airport, you'll no doubt be used to the smell of kerosene when the wind blows the wrong way. But there'll be none of that with hydrogen.
Brilliant. No, thanks. So thanks very much, Stephen. So looking ahead to next year, what's exciting you? And then anything from your chat.
Yeah, I think the thing that probably excites me the most is exactly, and I don't wish to sound like a parrot, Simon, but I'm actually really excited by the opportunity that hydrogen presents. But more importantly, we have to do it. You know, Australia is in a position where, as I said earlier, we have this abundance of solar energy available to us. And if we can actually harness that to create green hydrogen, I think we have a real opportunity to move to a PTL-based eSAF a lot faster. One of the things that came out of the chat for me is that there's not enough biomass to be able to cater to the demand that we're going to need to have for sustainable fuels. And I think people are rightly concerned about impact on, say, the human food supply chain and just how much of this stuff actually is there. There is not going to be nearly enough to move the world's demand for sustainable fuels to biomass based. So we have to invest in getting PTL hydrogen based SAF up faster. Hydrogen eventually as a propellant, yes, but in the intermediate steps, it's going to play a tremendous role in allowing Australia to produce vast quantities of SAF and other renewable fuels that I think really excite me as an opportunity. I just don't want to see that opportunity lost. You know, we're pretty good in Australia at producing things like fuels and exporting them so that others can actually take the value and add value to what we export, and then we have to import it back. We have an opportunity here to create a new industry around a new fuel, and I'd really love to see us harness that.
Yeah, no, that's great. Great to bring it back here as well in Australia. Alexander, you probably just a chance to breathe, and you've got lots of exciting things happening in those in your space with data and opportunities already coming through. What's the one thing we should be aware of over the next year that people outside your direct area should be on the lookout for?
So first, in the long term, I would concur with Stephen and Simon. I believed in power to liquid and e-fuels. Now, if I go back to data, I think what's exciting is that all the new aircraft that are going out of the assembly chains are much more connected. They have things we call AID, aircraft interface device, where applications like ours can consume the data of the aircraft in real time, just one way. We are not, of course, making any change to the direction of the aircraft, but we can consume the data, and when we go through the pilot to make changes. And if we look at the current landscapes, maybe only 5% of the aircraft have this kind of equipment, but all of them that are going out of the assembly chain have them. So I think it's going to be a lot of change, plus communication, between aircraft and ground, which is getting cheaper. I think these are two big trends.
Yeah.
Right. So we have maybe time for one more sort of topic, and I put it to all speakers, but I might start with you, Alexander. It's about the safety, and everyone alluded to it. You talked about cyber safety, and I think that's very topical. And the other speakers referred to the necessary testing for new fuels and technology. So maybe if you can elaborate a little bit what's been done about that, how serious a threat is that? Alexander, if you want to start, maybe.
Well, sure. The safety of the data is very important. First, before cybersecurity, that's data which is very rich, where we analyze all the aircraft behavior and basically pilot behavior. So we make sure all this is fully anonymized and safely considered on each time we bid for an airline. We've been scrutinized with penetration tests and things like that. It's going to be even more true when we go to the connected aircraft. That's why also, usually data can only go one way, from the aircraft to the electronic flyback, and not the other way around. And a lot of people are working a lot of that. But I think it's fairly safe. It has to be, and there's lots of investment on that. Yeah.
Stephen, we lost your sound for some reason.
Yeah, sorry, have you got me back? Yeah.
Yes, wonderful.
Let me just add a couple of comments to this, if I may. I think I touched on safety as a really important factor in the development here, and why we also have to be a little patient sometimes with the progress that's being made, because certification will take time, and we have to understand exactly why that's the case. But I think this is not a concept that's new to us. I think even in a highly competitive industry like ours, whether it's the airlines that are facing customers, people like you and I, or whether it's the manufacturers facing the airlines, we are all very competitive. But one thing we're not competitive on is safety. The amount of work that we do with our colleagues at Boeing and Embraer and the airlines that all harness improvements in safety, learnings, and making sure that next generation products build the most advanced safety features that we know, I think is actually very inspiring, and probably a lesson to a lot of other industries. And I do see this. Maybe others don't because they're not inside the industry, but the amount of time we all spend on safety with each other, even in a highly competitive world, is actually really inspiring to me.
Any additional thoughts, Simon, on safety, or otherwise back to you, Tim?
Yeah, I mean, very much as Stephen was saying, safety, if you're in the industry, safety is top priority always. It's almost that unsaid priority. It's just by assumption. We shouldn't be complacent, of course. Changing to, bring in any new technology, you do need to make sure it's thoroughly tested out, thoroughly demonstrated. And, unfortunately, there's a huge amount of excitement generated by social media, and people, get all upset that new technologies don't happen faster. But believe me, there's one thing that will stop new technology dead, and that's if, there is a safety issue with it that's found once it enters service. So it makes absolute sense to step carefully and to make sure you understand all the risks, all the issues, and you mitigate them before you put stuff into service. Thank you.
Maybe, oh yeah, Tim, you're good to go.
Yeah, I'm conscious of time. I think you should just probably close it up, Suzanne, I think. But no, that's been fantastic from all the speakers. Thank you.
Well, I actually have 1 minute, so I will pick up the very last question that was, is it time for carbon tax? Every speaker briefly, yes, no, maybe. Alexander, would you like to start? Do we need a tax on aviation?
I think there is already, it's not really a tax, but there's a thing called emission trading scheme, which is already in place in Europe, and airlines have to buy allowances for all their carbon emissions. That is for intra-European flights. And we have Corsia that is kicking in 2024. 76 states will voluntarily offset some of their emissions. I think we should go further, but I think that's probably better than a tax, because you find ways to use market-based measure, I think.
Well, Simon?
Well, the interesting thing is, I've been involved in various debates. How do you pay for the transition? And it doesn't come for free. And should you pay for that by taxing everyone? Well, if I'm not flying, I'd feel a little upset about that, having to pay a tax to fund people to fly and decarbonize when they fly. So, there is some logic to taxing. One of the things I always think is that, we've done a fantastic job as engineers making aircraft more efficient and much, much cheaper to fly. I mean, the cost of flying is very, very cheap. Certainly in the UK, you can pay a lot more for car parking than it costs to fly on your airplane. So
Okay.
that's the crazy way that, you know, flying economics work at the moment. And so I think we do have to pay for the cost to the environment that we're
fair point.
departing.
And raise the funds for the transition. Very quick, Stephen. Yes, no, maybe.
Well, it's actually a very sophisticated conversation we need to have around the instruments that fund the transition. I think, as Simon said, all very well to put a tax on something, but where's the investment from government in generating the inputs for the sustainable fuels that we're going to need to take the decarbonisation journey forward? Yeah, have the conversation by all means, but let's make it a broad conversation about what we need to do financially to make this model work.
Great. I take that as a hint for next year's seminar. We have a whole session on how to fund the transition. With that, we wrap up. I thank all the speakers and also the participants for the questions and for you guys to answer them and engage in this very important discussion. Thank you so much. And remember that everything will be online if you want to rewatch it or share it. Thank you. And yeah, have a good afternoon or day, everyone.